Welcome back. In this video, we will see sufficient conditions on the function f(x) so that its Fourier series converges pointwise to the function f(x). Okay, so there are many sufficient conditions. So we will start with one sufficient condition on the signal, that is that's a piecewise differentiable function. That means it is a differentiable function. F(x) is differentiable, that means f dash of x exists, and that f dash of x is a piecewise continuous function. So let us take so if we have such a conditions on the signal f(x), so we will just show that the Fourier series composed of Fourier coefficients and the fundamental signals in terms of cosines and sines. So that Fourier series composed of all this gives you Fourier series. We will show that this series, this function series converges to the function f(x) pointwise. That means you fix x, then the function series becomes a number series. That number series converges to the value of the function at x. So to do this, if you have such a function, if f(x) is a piecewise differentiable function, then it has certain properties. So we will do that properties first. So let us consider let f of x be piecewise continuous period. So let us start with the piecewise continuous function. So one of the sufficient conditions we have is a piecewise differentiable function. So if it is piecewise differentiable function, implies it is a continuous function. So for such a function, piecewise continuous actually periodic function. So we only consider periodic functions, periodic function with period let us say L. Then what you have is this result. So this is called Bessel inequality. N is from minus infinity to infinity. This is your Cn's complex Fourier coefficients. This is less than or equal to 1 by L minus L by 2 to L by 2 absolute value, square of the absolute value of this signal into dx. This is what you have. So this is called Bessel's inequality. So we will first prove this as a theorem. Let us call this theorem, and if you prove first, we will first prove this and use this in the sufficient conditions to show the convergence of Fourier series of f. So we start with so you have once you have this Cn's as complex Fourier coefficients, so you have the Fourier series. So the Fourier series is Fourier series, this is n is from minus infinity to infinity, and you have Cn e power I n omega naught x, or omega naught is 2 pi by L, because it is a signal is of period L. So this is your Fourier series. So let us consider the partial sum of this. Partial sums, let us represent Sn of x. You take the partial sum of this series, that is, you take it from minus n to n, as it depends on n. So if I change this index as k, so it is running from minus n to n Ck e power I k w naught x. So this is your partial sum. So once you assume this is your partial sum, Cn is 1 by L integral minus L by 2 to L by 2 f(x) e power minus I n omega naught x dx. Okay. So if you integrate, integral minus L by 2 to L by 2 fx minus snx. This you multiply with e power minus in omega naught x dx. What is this value? This value is actually this is integral minus L by 2 to L by 2, expand it. So, this is f x e power minus in omega naught x dx minus integral minus L by 2 to L by 2 S n x. This you write it as k is from minus n to n c k e power I k omega naught into e power minus I n omega naught x, this with dx. So, this is nothing but this is your C n, and here this is your, so you can, this is a finite sum, you can take it out, k is from minus n to n c k, this is the integral minus L to L by 2 to L by 2, and what you are left with is e power I k minus n omega naught x dx. So, what happens when k and k is from minus n to n, when k is n, only when k equal to n or k minus n is non-zero, when k n minus n is non-zero, you can see that this quantity is same. So, it is going to be 0. So, when it is not, it is only when it is equal to 0. So, that is actually C n minus. So, let us choose this is equal to 1. For example, this is always a number. So, let us take as 1. What happens to minus L by 2 to L by 2 e power I omega naught x dx. What is omega naught? Omega naught is 2 pi by period is L. So, this is equal to I omega naught e power I omega naught x, for which you take this L by 2 to L by 2 limits, you apply, you get e power I times omega naught is 2 pi by L into x is at L by 2. So, 2 goes L by, so e power I pi minus e power again minus I pi. So, what is this one? This is actually e power I pi is cos pi is minus 1, and here also minus of cos pi is minus 1. So, it is going to be plus 1, which is 0. If it is 2, if I take any n value here. So, if k minus n is some number, say let us say some L, which is non-zero. So, what you have is I L omega naught. So, you have I L omega naught. So, you still have I L omega naught I L pi. So, when L is integer, so this is still minus 1 power minus L n power L, okay, into minus of minus 1 power L. So, it is any case it is 0. So, you can see that when k minus n is non-integer, non-zero integer, this is always 0. So, this quantity is 0. So, everything else will go except when k equal to n. So, that is corresponds to C n, and in that case this will be e power 0, that is 1. So, you have L by 2 minus L by 2, that is going to be, of course. So, this is not exactly C n, C n is L into C n. So, you have L into C n, this is actually by definition this is the Fourier coefficient L into C n, 1 by L of this is C n. So, you have L into C n, and here C n can k equal to n, it contributes integral minus L by 2 to L by 2, can k equal to 1, this is 1 dx, that is L. So, finally, it is 0. Okay. So, we see that we observe that this is the case, f x minus S n multiply with e power minus I n omega naught x, that quantity is 0. So, because of that we note that minus L by 2 to L by 2 f x minus S n x So, because you multiply any of this quantity, okay. So, what is your Sn? Sn is this, you take any of this quantity, that is 0, okay. So, instead of, so you take a linear combination of them, so that is Sn. I have chosen minus of this. So, Sn is with plus. So, you can just take Sn bar, that will have exponential with minus I sign. So, Sn of x conjugate of this dx, this is nothing but sigma k is from minus n to n. So, Sn's you can replace, so C k bar. So, integral minus L by 2 to L by 2 f x minus S n x, that is as it is, into e power minus I k omega naught x dx. Now, this is exactly what we have seen, that it is 0. Okay. So, this is this simply in the place of n you can put anything k. So, it does not matter. So, you have, because this quantity is 0. So, what you have is every time it is 0, whatever may be k value, it is 0, this quantity is 0. So, that means it is completely 0. So, we first note this one, then we observe that if you simply integrate from minus L by 2 to L by 2 f x minus S n x, and this is a complex quantity, and you have f x bar minus S n x, the conjugate of this whole thing, that is actually absolute value square dx. This is always positive. Okay. So, and what is this one? This is actually equal to minus L by 2 to L by 2, and because this with Sn bar, that is 0. So, you are left with only f x minus S n x into f x bar dx, which is, that is always, this is same as this, because the other part will be as is shown to be 0 earlier here. Okay. So, this is equal to integral minus L by 2 to L by 2, this is f x into f bar, that is mod f x whole square dx minus L by 2 to L by 2 S n x f of x bar dx. Okay. And you can also observe here, this gives, we have noted that this quantity is 0. Okay. This quantity 0 implies minus L by 2 to L by 2 f x S n of x bar dx is nothing but minus L by 2 to L by 2 S n of x bar modulus square dx. Okay. So, that is exactly we write here. So, this is equal to minus L by 2 to L by 2 f x bar modulus square dx minus, this is L by 2 to L by 2 S n of x square dx. And clearly, this quantity is a positive quantity. Okay. And what is this one? So, integral minus L by 2 to L by 2 mod S n of x, or rather S n x into S n x bar dx. If you write this, you actually see that this is quantity k is from minus n to n c k e power I. So, what is this S n? S n you define as e power I k omega naught x. Into its bar. So, that is C k bar. So, rather this into, now I change this as different, that is index, as index you can write in a different way, or you can use the same index minus n to n C k bar e power minus I k omega naught x dx. This is what it is. This is Sn x, this is Sn bar x. This is equal to, so only contribution is when they are equal, when they are same, that is, and so integral from minus L by 2 to L by 2, any exponential function when this one and this is different. Okay. So rather let us use a different k, different. So I use from this, instead of this index, I use a different index, that is, let us say m. So this m is from minus n to n. So this is a product of this finite sums. As well, so as long as this exponential you multiply this with this, you get e power I k minus m. When only when k equal to m, that is becoming e power 0. So that is I times 0. That is the only contribution you will have. Otherwise, that integral is 0. That is what you have seen earlier. So what you get is sigma k is minus n to n c k mod square. Only when m equal to k, that is what is the result, and it will become 0. So that is exactly you will get. So the integral will be simply L. So each one, so you have this is minus L by 2 to L by 2 dx. This is nothing but L times sigma k is from minus n to n modulus of c k square. This is what you get. So this implies sigma k is from minus n to n modulus of c k square is you can replace this quantity here minus of that. So if you use this inequality, 0 less than or equal to integral minus L by 2 to L by 2 mod f of x whole square dx. In the place of this, now I will replace this. So that is actually L times minus L times sigma k is from minus n to n c k square. This is true for every n. Okay, so this implies you can bring this side. So you get sigma c k whole square, k is from minus n to n, is always less than or equal to 1 by L integral minus L by 2 to L by 2 mod of f x square dx. So this is true for every n. Okay. So this implies because this is true for every n, you can allow this to be n goes to infinity. So you can see that this is actually true for every n. So that means you can allow n goes to be infinity. So you have, so k is from minus infinity infinity mod c k square is less than or equal to 1 by L minus L by 2 to L by 2 mod f of x square dx. So this is exactly what you want to prove, that is Bessel's inequality. So which you can see here, this is your Bessel's inequality. So this is what we are going to use to show that if the signal is piecewise a differentiable function, and we will show the Fourier series actually converges. So in the process, in the proof of that, we will use this inequality. So one important corollary of this, one implication of this result is that, so if this quantity is the right hand side quantity is finite, that means if f of x is so, or if minus L by 2 to L by 2, if it is square integrable function dx, if this is finite, okay, then this quantity n is from minus infinity infinity. I am just changing the index here. So c n square d is always finite, that means. Okay. So what does this mean? So this means, that implies, that's clear, right? This is straightforward. If this is finite, this is finite, that is what I have written. So this implies a limit of c n as n goes to infinity, this is going to be 0. So, this is straightforward from the number series. If limit of if sigma a n is from 0 to infinity or minus infinity infinity, if this quantity is finite, then this limit of a n has to go to 0. If it is not, see, the proof is why is this so? So, we will use contrapositive argument that if limit of this is non-zero, if suppose this limit a n is not equal to 0, okay, then what happens? So, this converges to some non-zero quantity, some L, okay. Then what is the result? A n minus L, you can put them in some arbitrary small quantity whenever n is bigger than some big N, okay. So, that means A n is always lying between L minus epsilon to L plus epsilon for every n bigger than or equal to n. So, you can choose epsilon as 1. So, so you can choose any epsilon. Given epsilon, there is a big N that depends on n. So, given epsilon, there is an n beyond which these a n's will strictly lie here. So, if you choose epsilon as 1, you have your a n's will be lying so for some n. N is this capital N is actually depending on what you give as epsilon. Here we have given as 1. If L is non-zero, let us say you can think of L as L is a positive quantity. So, let us choose positive quantity. So, I assume that L is positive. So, I can choose epsilon as L by 2, okay. So, if I choose L by 2, there exists corresponding some n beyond which you have L plus L by 2. So, this is because L minus L by 2, this is always positive. So, this implies sigma a n, because these are all positive quantities, you are adding up every time, okay. So, for n is running from 0, so a 0, a 1, every time you are adding a positive quantity all the time. So, this has to go to infinity, but that is not the case, but we know that this is actually finite. So, that is why, so that means this has to go to 0. This is a small result in the on sequences series of real numbers. So, using that, you can see that this is a limit quantity has to go to 0. So, this is a Riemann-Lebesgue lemma, this is a Riemann-Lebesgue okay. So, now we state this sufficient conditions as a theorem, main result that if f of x is a piecewise differentiable function, periodic function, with period L, then this what you have is this Fourier series, complex Fourier series, which I am writing as Cn e power I n omega naught x. Omega naught is the fundamental frequency, which is 2 pi by L, okay. This is equal to, it is actually converges to the value, once you fix this value x, this converges to half of f of x plus. That means, if you have this is your x on the real line between minus L by 2 to L by 2, x plus is a limit of f of x plus is a limit of f of t. Now, t is going to x from the positive side, that is the meaning. So, the limit of this function as t, if it is t is here, t is approaching x right hand side. Similarly, f x minus is a limit of f of t, t is going to x, a negative side. So, this is the meaning of these two function values f x plus and f x minus. So, whose average value is what this series converges to that. If you fix your x I fix maybe inside, okay, because it is a differentiable function, it is a continuous function, implies it is a continuous function. So, f x, so you can always choose like that. Okay. As of now I am choosing x in between here, so not at the end points. So, if it is an end points, it is actually we will see what it is. Okay. So, x belongs to minus L by 2 to L by 2. So, let me give you the proof now. This is the sufficient condition for this Fourier series converges to the function. Because it is a differentiable function, this is actually you can say that this is exactly equal to f x, because this is nothing but f x because of its continuity, both are same. So, average value is itself. So, x belongs to minus L by 2 to L by 2. So, the proof is again we will consider the partial sums of this left hand side. So, partial sums we represent as n x, okay, as in the earlier case. So, you have k is from minus n to n c k e power I k omega naught x. So, this is equal to sigma k is from minus n to n c k. So, c k I am going to define. So, what it is? C k is the Fourier coefficient, that is 1 by L minus L by 2 to L by 2 f of t e power minus I k omega naught t, that is my c k, into this I write it as it is. So, this is with dt and e power minus this power, this is as it is, that is e power I k omega naught x. So, this will give me I take this sum inside. So, you have 1 by L minus L by 2 to L by 2 f of t, and now I write the sum here, finite sum, because it is a finite sum I can take it inside. So, what you have is e power minus I k omega naught t minus x dt. So, what is this one? This is equal to 1 by L. So, you can see this one, you can just replace, you can break this integral into two parts. First from 0 to L by 2 f of t, this finite sum, k is from minus n to n e power minus I k omega naught t minus x dt plus 1 by L minus L by 2 to 0 f of t sigma k is from minus n to n e power minus I k omega naught t minus x. So, what I do here is, so let us call this some quantity which is messy. So, let us define, let dn be, I will call it some dn of x. This is a function of x. Okay. So, let me define what is this dn of x. If I define it as k is from minus n to n e power minus I k omega naught x. If I define it like this, then what is this quantity? This quantity is actually equal to, so e power I n omega naught x, and I put k equal to minus n plus e power I n minus 1 omega naught x, and so on, will go on 0, that is 1 also somewhere comes in between, and then it is becoming negative. And I put n equal to k equal to n, is finally end up with I k is n I n omega naught x. So, this is equal to, if you take e power I n omega naught x out, so you have 1 plus e power minus I omega naught x, and e power minus I 2 omega naught x and so on. Finally, e power minus I 2n omega naught x. That is what is the thing. So, this sum you can, this is in GP. So, you can just have it. So, e power, you can write that sum with a is 1 into 1 minus r is e power minus I omega naught x power 2n plus 1. So, you have 2n plus 1. So, n is 2n here. So, n plus 1 is 2n plus 1 divided by 1 minus e power minus I omega naught x. That is what it is. So, if I now take it inside, so this is e power, this is the product for everything. So, if you take this inside, e power I n omega naught x minus e power minus I n plus 1 e power I n plus 1 omega naught x divided by 1 minus e power minus I omega naught x. What I do is, I take the denominator also I rewrite like this. I multiply e power I n omega naught by 2, e power I omega naught by 2x. If I multiply and divide I n plus 1 omega naught x divided by, so you also do it here. So, if I do both sides, so you take it inside, the denominator one you take it inside here. So, you have e power I omega naught 2x minus e power minus I omega naught by 2x. That is what it happens, it becomes. Now, take this one inside. So, what you see is e power I n plus half omega naught x minus e power is actually minus I n plus half this one. So, minus 1 minus I plus I become, that is minus half. So, that is what happens, omega naught x divided by this is actually nothing but this is as it is. So, I omega naught by 2x minus e power minus I omega naught by 2x. So, what is this one? This is exactly equal to sine 2I sine of n plus half omega naught x divided by sine omega naught by 2x. This is what is my dn of x. If I define like this as dn, dn is this. So, clearly dn of minus x is actually equal to dn of x. This is an even function, So, if you use this one, what happens to your Sn? Sn is this one. So, what happens to your Sn? Sn is Sn of x is 1 by L integral 0 to L by 2. So, what happens to f of t dn of, what is your dn of t minus x, dn of t minus x dt plus 1 by L minus L by 2 to 0 f of t dn of t minus x dx dt. That is also same, right? So, you can see that both sides are same. So, you just split that integral. So, this is what it is. Now, put t minus x as some x dash in this integral. If you do this, you have dt is dx dash, and that becomes, and here t minus x as first of all put t equal to minus t. So, in both the integrals you can put it as t minus x as x dash. Then what happens to Sn x? Sn x is 1 by L integral 0 to, so if I put t equal to 0, and this is going to be minus so t is t minus x is so if you need not split it before splitting itself, you can split it later. So minus L by 2 to L by 2, this is what is this Sn. You put this one, so you can see that it is going to be minus L by 2 minus L by 2 minus x, because x is fixed, to plus L by 2 minus x. Because it is a periodic, the translation will be same as again minus L by 2 to L by 2. So both will be same. So this will not change because it is a periodic function. So minus L by 2 to L by 2, f of t is x plus x dash dn of x dash dx dash. This is what it is. Now you can split this into two parts. So 1 by L minus L by 2 to 0 f of x plus x dash dn of x dash dx dash plus 1 by L times 0 to L by 2 f of x plus x dash dn of x dash dx dash. So what happens here? So here you change x dash by put some x dash by minus x minus t, if you say, if you do minus, so you get 1 by L, this becomes L by 2 to 0 f of x minus t dn of minus t, which is dn is the even function. So dn of minus t is dn of t, and you have minus dt. So that is minus this minus, so you can change the limits. So 0 L by 2. So t you replace as it is. So x dash itself. So actually this is what, okay, let us write dt only. So dt, and this one is plus 1 by L integral 0 to L by 2 f of x plus t dn of t dt. This is what you have. Okay. So this is exactly, it has become my Sn of x, the partial sum of the Fourier series. So the next step is you just write what is your dn of t, that is 1 by L 0 to L by 2. You can combine these two integrals. There is going to be f of x plus t plus f of x minus t. This one I wrote first, and into this plus this. So dn of t is common. So dn of t, we have seen already that this is sine n plus half omega naught x divided by sine omega naught x by 2. Okay. This is what we have. The this is a function of t, so you write t dt. So what I do is I do a small trick here. I just add and subtract, because so I am going to assume that this quantity is one function. Okay. This is one function. If I take this as one function, so you will see that. So what we are going to show is, eventually maybe I will see in the next video, that I will show that if I choose if qn, so let us call this some qn of let us say quantity qn of t is f of x plus t plus f of x minus t. X is fixed, so that is why I am calling it t, function of t, and divided by sine omega naught t by 2. So if I call this as my function, this is this has to be well defined. Okay. You see that t is actually, so t belongs to 0 to L by 2. So that is what is the integral is between. So as t goes to 0, I have a trouble here. So this is 0 and this quantity, so something divided by 0. So that is why, to avoid this, something quantity, some quantity fx 2 times fx divided by 0, that is going to be infinity. So to avoid that, so I will just rewrite this q as f of x plus t minus, and I have x, a positive side function. Okay. and then plus f of x minus t, I will also subtract a negative side function divided by, I divide with x, so that I have to multiply x divided by this sin omega naught t by 2. Okay. This is what I will do. Okay. So, this integrand value, this is what so because I added and subtracted, so I will have to add, I will have to take, I will have some addition, that is fx plus fx minus, because I subtracted both sides, both times xx I do not use, divided by sin omega naught, I have subtracted only this one, right. So, okay, so we will see maybe in the next video, we do not have time. So, from here we will go on next, we will see in the next video. We are trying to prove that the Fourier series converges to the function f when it is a piecewise differentiable function. So, we are halfway through, so we have taken the partial sum of this Fourier series and we manipulated up to some point. So, the remaining part to show that this actually converges to the function f(x) in the next video. Thank you very much.